delta. Is it that? Can you confirm for me, please? I think it's that. For over n. Sorry. Is it right, or maybe compared to the previous? I don't remember. It's okay. Yeah. Yeah, because now we have like divided by 4, and there's no 2 here. Oh yeah, there's no 2 there, right? So it's not log of 2 here, isn't it? Because this 2. Let me see. Let's open. I think it's better. Yeah. If we open it. Okay. So opening, we have delta equals to 2n f2n, because it's a composed by 2 samples. So in that situation, we'll have log on this side of delta to be equal of log of everything. So we have log of 2, yeah, perfect. Log of 2, and this guy will be inside. So somehow we will have plus log of n f2n, right? Mm-hmm. Minus n. Oh yeah, I think it was right. Okay, but anyway, we do it again, no problem. So here we have, okay, now we can say log of delta minus log of 2 minus log of the shattering coefficient for 2 samples is equal to minus n epsilon squared over 4. And that will be the same as 4 minus 4 over n being multiplied here, right? Mm-hmm. I have to remove it from here. Okay, and now we have the the squared root. Yeah, it's right. Mm-hmm. So now we can do from this. We finally have the expected risk to be smaller than or equal to the empirical risk of f plus this term. I prefer this term as a positive term because it makes it easier to understand what's happening. So I prefer it like 4 over n multiplied by minus log delta. Let's put the things that are positive at the beginning. And the most important thing is the shattering coefficient. So the shattering to start. Then plus log 2 and minus log delta. Yeah, it's that. So now the main conclusion we have is we shouldn't be just assessing the empirical risks. We should somehow assess also the complexity we have for the biases. That's very important. But there is something else. Let's suppose that my shattering coefficient is exponential. Let's suppose it is exponential. What would be the result if it is exponential? What happens? Let's say it is something like 2 powered 2n.
So the ends go away.
The ends will be cancelled. Yes. The ends will be cancelled. Here we have log of 2, which is, of course, greater than log of delta. But what's delta, in fact? Coming back, we see this term on the right side was made equal to delta. What that delta means, so just take a look, what that delta means, should mean. if delta is equal, for example, to 0.5, this basically means that I want the probability of having this difference greater than epsilon happening just for 5% of the cases. In 95% of the cases, I don't want it to happen. So this works as some level of confidence. Some level of confidence. That's a confidence level, actually. So when I can see delta as some sort of term that ensures an upper probability. So if I say I want this to happen just in 1% of the cases, this would be 0.01. And if this guy is 0.01, it's so small. When I apply log, right? And I already have like here log of 2. What's going to be the result here? It's going to be log of 2 divided by delta, actually. Will I have some sort of upper bound here? No. This guy is not defined. So as it's not defined, will I have some sort of learning in that situation if my space of admissible functions, if my bias is two-way complex? No. I have no way of ensuring it. So if it's too complex, my bias, there's no learning bound. There's no learning guarantee, actually, because the complexity is so amazing. That makes us remember probably the Occam's razor principle. That makes us remember from statistics the parsimony principle, where somehow we should have some balance in between the complexity of the space and the result we have here. I mean, the quality of the result we expect. So it's not just about analyzing the quality, but also analyzing the complexity. Of course, if I use the k-fold cross-validation and I show people the standard deviation, I am already implicitly showing that my complexity is not amazing. But we see many papers where people just show the average. Just show the average of the k-fold cross-validation. Haven't you? Is that fair? I mean, no, it's not. Because I have no idea about the complexity of the space. If the space is too complex or it's not. Could be a simple space. Exactly after that, you know what's interesting? This, if you guys look for the Tikhonov regularization, if you guys look for back learning by Valiant, right? And if you guys look for the random macro complexity, it's the same. So different people in different moments in time found out the same inequality, that we have to have some sort of balance between the complexity we have for the space of divisible functions and the result we have in a given sample to ensure some bound for examples we have never seen yet. But probably we're going to receive those examples, and we expect that our classifier F or our regressor F works well in that scenario. But to have that, it's not just enough to have some good result in a given sample, but we also have to have some space of divisible functions, aka bias, that's not too complex. Something else. And that's only ensured only if my joint probability distribution is fixed, is static. that's only insured, again, I think you remember from the first lecture, if my data is IID. So if you guys think, okay, but I'm gonna use that to learn time series, if you're gonna use data a long time, and it's gonna probably have some sort of dependence, this is not insured. It's not insured. You have to do something else. You have to give another step to make it work, to make it, I mean, you could have good results, but is that meaningful? If you don't do something else, what can you do? Of course, you can apply some sort of transformation on data to ensure data is IID. That's something I've been working a lot, like for the last 10 years, I'd say. And something else, JPD must be fixed. So if my data distribution changes along time, what means basically is that maybe on this side of the room, I have a bunch of sand, and along time, that sand goes to the other corner. Is it fair to say that I have a good result if I'm just assessing for this pile of sand, and afterwards the sand is not going to be here, it's going to be there, so the behavior is completely different. So I have no bound, no learning guarantee in that scenario too. Again, that's a problem. I have somehow to characterize my data distribution. I have to have a good space. For example, it's R2, R3, R something, or it's not even R, it could be another space, could be a space of integers or something else. But is that space meaningful? Is that space telling me what's happening in that particular problem? After this, Vapnik with another lady called Corina, they worked together to build up the large margin bound. The large margin bound tells me something that's very interesting, very, very, very interesting. And it's so simple to explain. It's so neat. It's this. If I have a bunch of points in a given space, and those points are very far from the negative points, if I build up a hyperplane here, having the largest as possible margin from both data sets, from the positive and from the negative side, this is the margin, or this is the margin if you prefer, because both should be equal, right? Not numerically equal, because there's some, of course, there's some variation when you're computing. You have the smallest as possible shattering coefficient. That's the main conclusion of that. I can write down that bound, but what's the most important is that as soon as I found out some space, what I have some data distribution from the positive side and another from the negative side, which are very, very far from each other, I reduce the shattering coefficient. If I reduce the shattering coefficient, I reduce the complexity. If I reduce the complexity, I need less data to ensure learning. I need less examples to ensure my classifier or my regressor are indeed working in practice. That's so, I mean, yeah, almost time. That's so interesting, right? I'm just gonna write down here something, just to remember this. And then I don't even know if we should go next step. I think we could define what we're gonna do next. I think it's better if you do that. for the next Friday. So next Friday, I'd like to discuss with you this, just this. There's an equation. You guys let me know if it's wrong or not. I think it's right, but let's remember it's like log of 2, right? Minus log of delta. Okay, so that's a point. So I can look to that generalization bound. Generalization bound as the best as possible way to analyze learning guarantees, in the sense of classification and in the sense of regression. It doesn't work, of course, for unsupervised learning because it's not unsupervised. We have a loss function to compute the error, so there's no way of using that directly to unsupervised learning. Again, this delta is the same as, okay, here I had the supreme value of the empirical risk as an estimator for the expected risk given epsilon, and this is smaller than or equal to delta. So delta means the confidence level I want to ensure during learning. What's the confidence level I want to ensure? Of course, if I define delta to be equal like 0.5, it's going to be easier. But if I define it to be very small, and as small it is, of course I will have some impact here, right? Because this is going to be the log of 2 divided by delta. And if delta is very, very small, if delta approaches 0 somehow from the positive side, this turns out to be infinite. So I'd have like a log of infinite, and that's a problem, right? Indefinite, it's impossible to have that in that scenario. That makes interesting to observe that it's just impossible to ensure 0. It makes impossible. Something else, just a next step. How can I understand if this term provides learning to me? In other words, what's the most important term? We have a square root of 4 times the log of something divided by n plus log of 2 divided by n minus log of delta divided by n. Let's assume delta is greater than 0 because equals 0 would be a big problem, right?